Okay, so we've got a couple of simulations which we've been playing around with today. They can be found here. If you click on it, you click on that bit there, and it'll take you to the source. Same with that one there. And I've got a snapshot of one of the ones we were playing around with. So we've got this dog on a skateboard going up and down on this ramp. We can measure the height, but it also, if we take this little thing here, we can just click on it and it will tell us the height anyway, and it tells us the speed. And if we look over here, we've selected it to be 100 kilograms, quite a heavy dog, and then we've
Yeah.
put it on Earth. And the strength of gravity on Earth is 9.8. Now you can measure that in newtons per kilograms, like I did, or meters per second squared. It is the same number, but I won't go into why that is at the moment. Now, to calculate the gravitational potential energy, you just do mass times the strength of the gravitational field on Earth, or otherwise known as gravitational field strength, times height. Symbol for mass is m, the symbol for the gravitational field strength is little g, and the symbol for the height is little h. So all these are lowercase letters. And I've made a note of what they are here from what we've got in this picture here. Putting that up through our calculator and rounding up, we get 1,166 joules. Now, that's a little bit different to what they've got. They seem to have a rounding error. So although it says the height is 1.19 meters, that's three significant figures, whereas this is 1, 2, 3, 4, 5 significant figures. Sorry, well, this one's 5 significant figures. So they've made a that's not very good practice of them, really. So in other words, the height won't be exactly 1.19. We don't know what the height is. If we have to just assume, is it really 100 kilograms, or is that inaccurate too? So not ideal, really, but you can at least see that it's very similar to what they've got. We then calculated the kinetic energy, which is half times the mass times the velocity or the speed squared. So in this case, it would be 0.5 times 100, and the speed, it says 5.78, so 5.78 squared. And we get 1,670. Again, very close to what they've got there, but not quite the same. Again, it's going to be because either this is not quite right or that this is not quite right. Now, so that's basically how you calculate the kinetic energy and the gravitational energy. I think it looks like we've got just enough time for me to briefly talk about how to calculate elastic energy. So I'll include that in the video. Let's imagine we had a spring, it's usually a spring, that has been stretched by a force. So we've applied a force downwards. The spring has been extended by this amount. So this is the extension. In other words, this up to here would be its normal length, okay? So this is its normal length. And this extra little bit is how much it is extended by. Now, different springs are harder to stretch than others, right? We can think that depending on how thick the metal is, if it's really thick, it's going to be harder to stretch, and also depending on what metal it's made out of, and so on. So a measure of how difficult it is for the spring to be stretched is called the spring constant. So let's make one up here. We'll say the spring constant for this example is 5, and then it's going to be newtons per, and you could say per centimeter, but really you want to be converting it into per meter. So we're going to keep ours simple, 5 newtons per meter. Now, actually, that's really small. So I'm going to change that to 50, and it's still quite small. What this means is I have to apply only 50 newtons to stretch it by another meter. I think I might actually include it to 500. So 500 newtons would cause it to be extended. Let's imagine that I've only extended it by 5 centimeters. Maybe I'll use a different number than 5 just to reduce the confusion. 4 centimeters. 4 centimeters. I want to have that in meters. I divide it by 100, and that gives me a number in meters. How do I calculate the energy, the elastic energy? Then I'll call this EE. little lowercase e for the type of energy we're talking about, which is elastic energy in this case. So I'm just going to tidy this up a little bit because that doesn't look like much of a capital E there. Okay, all right. So elastic energy is equal to half, similar to the kinetic energy equation, half times the spring constant, which has got a capital K. So lowercase k, and times the extension, which is an E. Okay, so the extension has got a symbol E. Sometimes the symbol X, but nowadays it tends to be E, and that's squared. Very similar, isn't it? Very similar to the kinetic energy equation. So we're going to put these numbers in now. So it's half times 500 times 0.04 squared. We'll see how much energy does this spring store when it's when this particular spring has been stretched by 4 centimeters. 0.04 squared. Okay, so it's still pretty weak, really. Only when I've stretched it by that, it's only storing 0.4 joules. Okay. Now, 500 newtons might be a lot of a big force, but a meter is a huge extension. So this is still a pretty low spring constant. Okay. Anyway, that sums up today's lesson. If we might want to do a bit more practice on this with lots of different types of questions. So maybe next week we could do that. Okay.